Good morning, class. Today, we are going to talk about Chapter 3, Part 2. Please have your calculator, a pen and pencil, the pre-printed notes, and some scratch paper if needed. The last thing that we talked about in Chapter 3, Part 1 was the joule, which is a unit that we use to measure energy. There is another unit that you can use to measure energy. It is called the calorie, or the kilocalorie, which is 1,000 calories. The calorie is defined as the amount of energy necessary to raise the temperature of 1 gram of water by 1 degree Celsius. Or if you will remember, Kelvin is the same as Celsius in magnitude, so 1 gram of water by 1 degree Kelvin. 1 calorie is equal to exactly 4.184 joules. Remember that an exact number is one that does not count towards significant figures. This 1 calorie equals 4.184 joules is an equality. We can use equalities to create conversion factors. 4.184 joules in 1 calorie, or 1 calorie has 4.184 joules. Example 6. How many calories are obtained from a pat of butter if it provides 150 joules of energy when metabolized? So we have 150 joules. We want to know how many calories is that. So which conversion factor do I want to use? A or B? Again, we want to get rid of the joules. So therefore, the joules should be in the denominator so that it will cancel. Therefore, conversion factor A is the one that will get us there. 4.184 joules per 1 calorie. Joules cancel and we are left with calories. So 150 divided by 4.184 is 35.85 calories. Now, again, this is an exact relationship, so we do not look at this in terms of significant figures. How many significant figures are in our original number, 150? The 1 and the 5 are, of course, significant. They're not 0. This last 0 is a trailing 0. There is no decimal point after it, so therefore it is not significant. So there are 2 significant figures, so our answer should have 2. Draw our line here. This is an 8, which is more than a 5, so we're going to round this up. We have 36 calories is our final answer. 36 calories. Nutritionists burn food in something called a calorimeter. A calorimeter is used to measure amount of heat. It's a steel container filled with oxygen and a certain amount of water, and it measures the amount of heat gained by the water, which is the same as the amount of heat lost by the food. So here we have a picture of a calorimeter. You have an insulated container with a steel combustion chamber. Inside the steel combustion chamber, you have a sample of food. This is burned in pure oxygen. It's lit using these pair of ignition wires here. A spark lights up the food. As that sample burns, it heats up the water inside the chamber. As the water heats up, we have a thermometer here. We measure the change in temperature from the starting temperature to the final temperature. That change in heat is equal to the amount of heat given off by the food when it's burned. Since a calorie is equal to the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius, we can use this information to determine how much energy was in the food. Nowadays, we have a set number of values. We say that there are 4 kilocalories per gram for carbohydrates, 9 kilocalories per gram for fats, and 4 for protein. However, before we came to this value, we used to use calorimeters to determine these values. So let's try an example. A whole cup of milk contains 13 grams of carbohydrates, 9 grams of fat, and 9 grams of protein. How many kilocalories does a cup of whole milk contain? So we need to look at our previous table. Our previous table said that there were 4 kilocalories per gram for carbs and protein, and 9 kilocalories per gram for fat. So we have 13 grams of carbs, we have 9 grams of fat, and 9 grams of protein. We're going to abbreviate those C, F, and P. We can use the information given to us on the previous page here to create conversion factors, as I wrote them here. There are 4 kilocalories per gram of carbohydrates and protein, and 9 kilocalories per gram of fat. So for carbohydrates, we can say 4 kilocalories per gram. For fat, it is 9 kilocalories per gram. And for protein, it is 4 kilocalories per gram. So let's add up each piece. 13 times 4 is 52 kilocalories. 9 times 9 is 81 kilocalories. And 9 times 4 is 36. Now, if we add all three of these values up, 36 plus 81 plus 52, we get a total of 169 kilocalories. You can do the same thing. If you go into your cupboard and get an energy bar, a protein bar, a candy bar, or any serving of food in your cupboard, you can look at the nutritional information, check out the number of grams of carbohydrates, fat, and protein. Using these values, if you multiply each by its respective value and add them up, it should add up within a small portion of error to the value listed on the nutritional information. So again, you can go into your cupboard, grab an item of food, look at the grams of carbohydrates, fat, and protein, multiply them by these factors, add all three pieces up, and it should, within a margin of error, add up to the amount of calories listed per serving on that package. Okay. Let's talk about specific heat. Specific heat is specific. It is different for different substances, meaning every substance has its own specific heat. It is the amount of heat that raises the temperature of exactly 1 gram of a substance by exactly 1 degree Celsius. So again, a few minutes ago, we talked about the calorie being the amount of energy necessary to raise the temperature of 1 gram of water by 1 degree Celsius. That is the specific heat of water. Now, as I said, every substance has its own special specific heat. The units of this are joules per gram per degree Celsius in the SI system and calories per gram per degree Celsius in the metric system. The formula to calculate the specific heat is the heat divided by the mass times the change in temperature. Again, the heat divided by the mass of your substance times the change in temperature. And the units should be in calories or joules per gram per degree Celsius. Again, for water, it is 1 calorie per gram per degree Celsius, or 4.184 joules per gram per degree Celsius. Let's try an example. Example 8. What is the specific heat if 24.8 grams of a metal absorbs 275 joules of energy and the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius? Again, specific heat is equal to the heat, which we are given as 275 joules, divided by the mass. Remember, mass is a measure of weight. We have 24.8 grams times the change in temperature. Now, the change in temperature is always going to be the final temperature minus the initial temperature. The final temperature minus the initial temperature. The final temperature is 24.5 degrees Celsius minus 20.2. Again, if you are putting this into your calculator as one equation, please ensure that your denominator has parentheses around the whole thing, as well as that there are parentheses separating the 24.5 minus the 22.2 and the 24.8, so that you have the correct order of operations. Okay, 24.8 times parentheses 24.5 minus 20.2, close parentheses, and I get a specific heat of 2.58 joules per gram per degree Celsius. Again, none of our units cancel. We have degrees Celsius here, degrees Celsius here, joules, grams, degrees Celsius. None of our units cancel. So our answer is 2.58 joules per gram per degree Celsius. Matter undergoes a change of state when it is converted from one state to another state. Remember that our states of matter are solid, liquid, and gas. So when going from a solid to a liquid, you have undergone a change of state. A substance is melting when it goes from a solid to a liquid at its melting point. It is freezing when it changes from a liquid to a solid at its freezing point. Water has a freezing or melting point of 0 degrees Celsius. The heat of fusion tells you how much heat is released or let go when 1 gram of liquid freezes. It is also the amount of heat needed to melt 1 gram of solid at its melting point. For any substance, the heat released during freezing is the same as the heat that you need to melt it. For water, the heat of fusion is 80 calories, meaning if you have 1 gram of water, to change that 1 gram of liquid water to solid water, you must release 80 calories. To go the other way, you must put in 80 calories. Okay? Or in joules, it is 334. This is in addition to the specific heat, which is the amount of heat necessary to change the temperature of a substance within the state it is already in. So, for example, to take a solid bit of water, otherwise known as ice, from one temperature, say negative 20 degrees Celsius, to warm it up to, say, negative 10 degrees Celsius, that is the specific heat. How much heat was necessary to take that solid from one temperature to another? The heat of fusion is separate. This is the amount of heat necessary to change the state. It has nothing to do with warming or cooling your substance. It is strictly the amount of energy necessary to go from solid to liquid or liquid to solid. So we want to know how many joules are needed to melt 32 grams of ice at 0 degrees Celsius. So we want to melt 32 grams of ice. How much energy do we need to do this? And we want our energy in joules. So we have 4 possible conversion factors. 1, 2, 3, and 4. We need a conversion factor that will get rid of our grams and give us joules. Since we are looking for joules, that rules out conversion factor 1 and conversion factor 2. Conversion factors 3 and 4 have joules in them. We need the one that has the grams in the denominator, since we wish to cancel out grams and get joules. That means that equation 4 is not the correct one. Equation 3 has grams in the denominator and joules in the numerator. So 1 gram of water requires 334 joules. We have 32 grams of water. So 32 times 334 gives us 10688 joules. That is how many joules are needed to melt 32 grams of ice at 0 degrees Celsius. Now, because this is a very large number, we may wish to report this in kilojoules. Does anyone remember how many joules are in a kilojoule? Exactly, there are 1,000 joules in 1 kilojoule. So we want to cancel our joules and report our answer in kilojoules. If we divide this by 1,000, we would get 10.688 kilojoules. Looking at our significant figures, we have three significant figures, so our answer should have 3. That would be 10.7 kilojoules, or 10700, 10,700 joules. Water evaporates when molecules on the surface gain sufficient energy to form a gas, and it condenses when gas molecules lose their energy and form a liquid. So again, we have two processes that are equal and opposite. It is evaporating when molecules on the surface of the liquid gain energy. When they gain enough, they become a gas. It condenses when those same gas molecules lose energy and fall back down to form a liquid. During evaporation, molecules of the liquid are converted to a gas at the surface. When water is boiling, all of the molecules acquire enough energy to form a gas or vaporize. As this happens, bubbles of water vapor appear throughout the liquid. So what is happening is we have water in here. All of the water has enough energy to form a gas. As this happens, you get little gas bubbles as water molecules throughout the liquid are forming a gas. They reach the surface and then escape as water vapor. Okay. When sublimation occurs, the particles on the surface of a solid change directly to a vapor. So this is from a solid to a gas directly. There is no change in temperature when this happens. When deposition occurs, gas particles go the opposite direction. They change directly to a solid, not through the intermediate liquid. Dry ice does this at negative 78 degrees Celsius. The heat of vaporization is the amount of heat necessary to change 1 gram of liquid to a gas at its boiling point. And it is the amount of heat released when 1 gram of gas changes to liquid at the boiling point. For water, this is 540 calories per gram, or 2,260 joules per gram. Notice this is much higher than the last value that we looked at, because again, we're going from a liquid to a gas. That requires more energy than going from a solid to a liquid. So the heat of condensation for water is the heat released when 1 gram of steam changes to water. This is 540 calories per gram of water, or 2,260 joules per gram of water. So let's look at another example. How many kilojoules are released when 50 grams of steam from a volcano condenses at 100 degrees? So we have 50 grams of steam meaning a vapor, so we are going and we are condensing, so we are going from a gas back to a liquid, okay? And we want to know how many kilojoules are released. So 50 grams of steam. Again, we have 1, 2, 3, 4 possible conversion factors. We want to go from grams to kilojoules. We don't have any kilojoules, however, we do have some joules. Since we are going to go to joules, that rules out the calories and leaves us with 2 possibilities, 3 or 4. We want to get rid of the grams and get an answer in joules. So that rules out number 4. Therefore, we're going to use conversion factor number 3, which says that 2,260 joules are released for every 1 gram of water. So our grams cancel and we're left with joules. Now the question asks us how many kilojoules are released. So we need another conversion factor. We need to go from joules to kilojoules. How many joules are in 1 kilojoule? There are 1,000 joules in 1 kilojoule. So now we're going to put this in our calculator. We have 50 grams times 2,260 tells us that there are 113,000 joules, but we're going to divide that number by 1,000 to get us into kilojoules, and we get 113 kilojoules of energy. 113 kilojoules of energy. There are 3 significant figures in the 50.0 grams. This is an exact value, so we don't worry about sig figs. And there are 3 significant figures in this conversion factor. So 3 significant figures is good enough for our answer. 113 kilojoules. Okay, now we're going to put this all together. We're going to calculate the total heat in joules needed to convert 15 grams of liquid ethanol at 25 degrees Celsius to a gas at its boiling point of 78 degrees Celsius. Ethanol has a specific heat of 2.46 joules per gram degree Celsius and a heat of vaporization at 841 joules per gram. Again, remember, specific heat refers to the amount of energy necessary to raise the temperature of something without changing its state. So specific heat, we're going to warm or cool a substance with no change in state. No change in state. The heat of vaporization or the heat of fusion, those things are the energy necessary to deal with the change in state. Change in state. Okay? So we need 2 pieces. We're going to use the specific heat to deal with warming the liquid ethanol. Okay? And we are going to warm it from 25 degrees to 78 degrees. So we have 15 grams of ethanol. Its specific heat is 2.46 joules per gram per degree Celsius. Remember that the equation for specific heat, the specific heat is equal to the heat divided by the mass times the change in temperature. In this case, we know the specific heat is given to us. We know the mass, that's the 15 grams. We know the change in temperature. We're going from 25 to 78. What we don't know is the amount of energy necessary to do this. So to solve for heat, you would multiply both sides by mass. Right? Mass cancels. And multiply both sides by, let's change colors here, by change in temperature. Oops, I did not want to put that underneath. Put it up here. Multiply both sides by change in temperature. So those cancel. And you're left with specific heat times mass times change in temperature equals the heat, which is what we're looking for. So we have the mass, the change in temperature. We are going from our final temperature of 78 degrees Celsius to 25, which was our initial. Okay, that's our change in temperature. And our specific heat was given as 2.46 joules per gram per degree Celsius. So our grams cancel. Our degrees Celsius here are going to cancel. And we're going to be left with an answer in joules, which makes sense since we're looking for an energy. So let's try this. 15 times, again, make sure you put your parentheses in, 78 minus 25, end parentheses, times 2.46. gives us an energy of 1955.7 joules. Okay, I'm going to round this here before we take the next step. We had 3 significant figures in this number, 3 in this number, 3 in this number, 3 in this number. Our final answer should have 3. This would be our line here. That 5 means that we round up, so we have 1960 joules. Okay, now let's take a look at the second piece, and I'm just going to erase this stuff at the bottom here so we have a little bit more room. Let's take a look at the second piece. The second piece is the amount of energy necessary just to change the state. So the first piece that we found up here is the amount of energy necessary to warm a substance up without changing state. The second piece, the heat of vaporization, is going to tell us how much energy was necessary to change the state. The heat of vaporization is 841 joules per gram. We had 15 grams. So we are going to multiply this by a conversion factor. There are 841 joules per 1 gram. So we're going to put our 1 gram on the bottom in order to cancel it out. Our 841 joules on the top. Grams cancel, and this tells us how many joules were necessary to change the state of our ethanol. 841 times 15 gets us 12,615 joules. Again, significant figures, we've got 3 and 3, we need 3 here. So this is going to be 12600 or 12,600. Now for our final answer, we need to add the 2 pieces together. The top piece, which was the energy necessary to warm the substance up, and the bottom piece, which was the energy necessary to change its state. So 1960 plus 12600 for a total of 14560 joules. You might notice that it takes a lot more energy to change the state than it does to warm up the substance. Again, changing state takes more energy than simply warming up a substance. This concludes Chapter 3, Part 2. Thank you for listening, and I hope to see you for Chapter 4.